Hello, my name is Muhammad SYAHMI bin MURAD. Today I want to present about Laboratory 2. Moving on to the foundation of my study, I formulate our research question: how does distance affect the amplitude of a wave signal? To answer this question, I established two primary objectives. First is to investigate the relationship between the distance from the wave source and the amplitude of the received wave signal. Second is to determine how the amplitude changes as the distance between the wave source and the receiver increase. To keep my experiment controlled and accurate, I define my My independent variable is distance between the wave source and the receiver. My dependent variable is amplitude of the wave signal. Based on this factor, my hypothesis statement is if the distance between the wave source and the receiver increase, then the amplitude of the wave will decrease because the wave energy spreads out over a larger area as it travels. Now, let's take a look at my experimental setup to see how I put our variable into practice. To measure how sound wave amplitude change with distance, I use a very simple control and accessible physical arrangement which you can see in the diagram here. I only required three main pieces of equipment for this experiment. First is a tablet. This serves as my sound wave source. Second is a measuring tape. This is crucial for controlling my independent variable. It allows us to precisely measure and adjust the exact distance between our source and our detector. And third, a smartphone. Placed at the other end of the measurement tape, the smartphone acts as my receiver, utilizing an audio recording application to capture the incoming sound wave so I can analyze its amplitude. Moving on to my experimental procedure, here is how I systematically conduct the trial. First, I set up the wave source using the tablet speaker and align it directly with the receiver, which was the smartphone microphone. To ensure my data stay reliable and fair, I fixed the wave source at a completely constant frequency and volume power throughout the entire test. Next, I placed the receiver at an initial starting distance. From there, we increased the distance at fixed control intervals, specifically measuring at step 0, 5, 10 and 15 centimeters. At every single one of the intervals, I record the incoming audio signal to actually extract and analyze the precise amplitude values from this recording. I import the wave data into Scalab coding for digital signal processing. Finally, I make sure to prioritize safety precaution during the testing. Because I were working with continuous audio frequencies, I keep the sound level strictly below any harmful hearing limits to protect my ears. Additionally, I made sure all hardware and charging connections were secure to prevent any electrical or equipment hazard. Now, let's take a look at the result that I collected. Starting at 0 centimeters, I established our baseline measurement. Here, the raw amplitude was its highest point of 0.405 with zero attenuation. As we move the receiver out to 5 centimeters, we immediately observe minor signal attenuation. The amplitude dropped by about 0.102, which translates to roughly a 25.19% loss in signal strength. By the time I doubled that distance to 10 centimeters, the drop became much more significant. The raw amplitude decreased to 0.275, meaning I lose nearly a third of our original signal strength, sitting at 22.10% attenuation. Finally, at the maximum test distance of 15 centimeters, we hit our lowest recorded amplitude of 0.155. This represents an amplitude drop of 0.250 from our baseline, resulting in an substantial 61.73% percentage attenuation. Looking at the data as a whole, it clearly shows a continuous downward trend. As distance increased, the signal attenuation increased significantly, perfectly aligning with our initial hypothesis. Now that we have seen the raw data result, let's dive into how I actually processed those recorded audio files. To ensure the measurements were precise, I developed a data analysis pipeline using Scalab. On the left, you can see the visual waveforms generated for each distance, and here is how I could process that information. The first step was audio data loading. We used the waveread function to import our recorded M4A audio files directly into Scalab. The function pulled two vital pieces of information: our digital signal amplitude values, which we assigned to Y, and the original recording sample rate assigned to Fs. Once the data was loaded, we performed waveform windowing. Raw recordings usually contain a bit of background noise or silence at the very beginning and end. To eliminate that interference and ensure a clean analysis, I cropped out a targeted segment of exactly 1000 data points, isolating a stable section of the wave. Next, we had to handle the timescale conversion. By default, the data are just a raw sequence of index number. To scale the graph correctly into real-world seconds, we established our horizontal time axis by dividing the sequence of sample points by our sampling frequency. Finally, we reached graphical plotting using the plot ty command Skylab. Rendered the visual waveforms you see on the left side of the slide. We then utilize standard labeling function like xlabel, ylabel and title to apply precise technical caption to each graph, giving us a clear visual representation of how signal peak amplitude visibly shrink as distance increases. To summarize my result, the experiment successfully tracked how distance changed the amplitude of a sound wave. As I moved from our baseline at 0 cm out to 15 cm, the raw amplitude dropped steadily from 0.405 down to 0.155. Looking at the percentage drop, the signal attenuated by roughly 35% at 5 cm, 22% at 10 cm and reached its maximum signal loss of nearly 62% at our final distance of 15 cm. Ultimately, these findings demonstrate a clear negative relationship between distance and amplitude. As the distance from the sound source increases, the received wave amplitude consistently decreases, which fully validates our hypothesis. Moving into the discussion, the data clearly reveals a definitive inverse relationship between distance and peak amplitude. To break this down physically, as we move away from our baseline maximum of 0.405, the peak amplitude dropped consistently at every single marker down to 0.155 at our furthest point. This tells us that signal attenuation has a very sharp upward trajectory early on, climbing rapidly to a 25.19% loss in just the first 5 cm, before ultimately scaling up to a substantial 61.73% loss at 15 cm. This rapid decay happens because the sound energy is forced to spread out across a much larger geometric area as it travels outward from the tablet speaker. Move on to the source of error. There is background noise, reflection from the wall and objects, and microphone sensitivity variation. For the limitation, the first one is limited measurement range and equilibrium calibration errors. For the implication, understanding sound attenuation is important in acoustic telecommunication, speaker placement, and environmental noise studies. Lastly, the conclusion is the experimental results support the hypothesis, as the distance between the sound source and receiver increased from 0 cm to 15 cm, the amplitude decreased significantly, confirming that distance has a direct effect on sound wave attenuation. That's all from me, thank you.